Hi there, welcome to your lesson on limits. Most students beginning their journey on calculus begin with limits. So that's where we're going to begin. Let's get started. Let's look at this together. Some sequences never stop increasing, like this one, while others eventually settle at a particular number. So imagine this sequence here going to infinity, it seems to settle at a certain number here. Or this sequence, if you follow it to infinity, also, even though it started going all over the place, it eventually settles to one number. If numbers in a sequence continue to get further and further apart, they are called divergent. If a sequence tends toward a limit, that means it seems to settle at one number when you go to infinity, it is described as convergent. So of these ones here, which are convergent, which are divergent? I hope you saw this one as divergent. It doesn't seem to settle at one number at all, it just keeps growing. This one is convergent, and this one is convergent. So remember again, when you go to infinity, if the function seems to go to one number, we say it has a limit and it converges. Okay, here's an example of a very famous convergent sequence. It's called the mean sequence. In a mean sequence, we have any starting numbers, first term, second term, then you find the average of those two. And the average is just adding, dividing by 2, gives you the next number in the sequence right here, 7.5. Then you find the average of these two, 6 and 7.5. And you get the next number in the sequence, and so on and so on. You keep taking the average of the previous two to find the next one. This produces a sequence that goes like this. Notice at first the numbers are quite different, but as you go towards infinity, the average or the next number in the sequence seems to settle in at one number, or a limit. So what is the limit of this sequence as you go to infinity? Well, hopefully, as you see, if you follow the graph here, it seems to settle in at the number 7, right? So we can write it like this. The limit as the x values, or this axis, goes to infinity, then the mean sequence, the limit of that mean sequence is 7. So here's where you put what's happening to x, and here's what you put what the function is approaching, or what is the y value that it's settling in on. Okay, but not all limits look at x going to infinity. Sometimes we look at x approaching some number that's not infinity. Let's take a look at this example. So here we have a function in blue, and we want to know what is the limit as this function approaches this x value, an x value of a right here. And let's say that value is 3. So we're saying what happens as you come towards 3 from both sides, and that's why we have these two arrows. What happens when you come towards 3 from the left side and from the right side? Do you approach the same y value? And let's say in this case that this value here is 7. So in this case, definitely, if you go from this side and from this side, you're approaching x equals 3 from both sides, you're coming in and converging on the same y value, which is 7. So here is the language of limits. We write it like this. We say the limit as x approaches some value and of a function, and it equals some limit value. So for this example, we have limit as x approaches 3, so we approach 3 from both sides, of this function, and we know the limit of that is 7 because it comes to 7 from both sides. Alright, so that's the basics of limits. Let's take a look at another example here. Here we have another function, and now I'm going to look at it. What happens when we approach x value, whatever this x value is, a. I guess it's 5, right? So as x approaches 5 from this side, we approach a y value of 3.8 because the function is here. And this is a weird function. It's kind of broken in half. But as x approaches 5 from this side, or x approaches a here, we get a y value of 1.3. So clearly when you come from either side, you're not getting to the same y value because the function is broken. So here's how you write x approaching a from the negative side, and here we have x approaching a from the positive side. And we get this limit when you come from this side, 3.8, and we get this limit when we come from this side. So those limits are not the same. Therefore, we say the limit of x approaching a, see now there's no plus or minus, it means just approaching a, does not exist. Because if the limits from each side are different, then we say the function as a whole does not have a limit at that x value. Pause there and just make sure you understand the details of that slide. It's important as we move on. Okay, so let's take some notes now. Let's do some examples together. But let's begin here. So we say the limit of a function as x approaches a equals L. This means that as the value of x becomes close to a from either side, we just saw that, for the function f of x, then the function f of x becomes close to a fixed value L. So if there is a limit, we see here that there is a limit, that means that from both sides it must approach the same value. So we write it this way, right? We show as x approaches a from the positive side, and we get to a value L. And then as x approaches a from the negative side, we get the same value L. Therefore, the limit of the function as x approaches a is that value, because it's the same value when you come from either side. So that is our limit. All right, let's look at some more examples. And again, there's the plus or minus thing. So let's begin with this one here. We have the limit as x approaches 2 of x squared. Let's begin by graphing this. So let's set the window in your calculator from -4 to 4, just like we see here. So let's set that window. Let me get the calculator ready here. Okay, so do it on yours as well. Set the window to match what we see here, -4 to 4, and then graph it. Okay, so notice I set the same window that we have here, -4 to 4 and -1 to 8. And then I entered the function, x squared, and now I'm going to graph it. So please do the same on yours. We should see a graph like that. We know this is a basic parabola. It looks like this. Okay, great. We have the graph. What's next? Well, it says check the table of values. Maybe you've never used this feature in your calculator, but basically we're going to use the table feature, and it's going to allow us to see specific points on the graph. So here's the graph, first of all, and we're trying to see what happens what is the limit when x approaches 2 from the left, from the right, right? So here's the x value of 2. We're approaching it along the function from the left and along the function from the right. We're converging in on this value of x of 2, and we're seeing what y value do we get to. Okay, so here's how you do the table feature in your calculator. So, and the table feature, notice we want to see these values. We want to see x is 1.9 and x is 1.99. In other words, we're seeing as x becomes really close to 2 from the left side, right? 1.9, then 1.99, it's getting really close. And then what happens when x is exactly at 2? And then on the other side here, we have what it's approaching from this side, right? So as x is 2.1, and then it's 2.01 means it gets even closer to 2. So notice how it's getting closer to 2 from either side. So here's how to do a table in the calculator. First, we're going to do set the table so that we can see values that are this small. So I'm going to go to second and then table set right here, which is like your window, but in blue. So here it says table start. You pick the starting value. I want this table to match the one I see here. I'm going to start at 1.9. So 1.9, and then this symbol means change in table. That means you're going to change the increment by which the table values jump, because by default, look, it has a 1. That means if I put 1.9, the next value would show me is 2.9 and then 3.9 and so on. But I don't want it to jump that much. I want it to jump by smaller values. So I'm going to put 0.01 as the jumping values, and you'll see what this means in the table. So now you're going to press second and table instead of graph, and instead of a graph, it's going to show you table of values. So here's my table of values. And you can see there's 1.9, so I know when x is 1.9, I'm going to put that value in. Okay, sorry. When x is 1.9, it's 3.61, and that's what I have in the table here. See, 3.61. And then when x is 1.99, we'll have to go down the table a little bit. When x is 1.99, I have a y value of 3.96, so that goes in here. And then let's go from the other side. So using your table, when x is 2.1, what's y? And when x is 2.01, what's y? So you can enter those two values in there. Hopefully you got the same as you see there. And then finally, when x is 2, I hope the calculator shows you a y value of 4. So we can see as we approach from the left and approach from the right, that means on the graph approaching both ways, the y values are both approaching the value of 4. So the function is approaching a value of 4. We can see it here. And that's clear. On this parabola, that makes sense. So we found that point, basically. We said as you approach that from both sides, you get a y value of 4. That makes sense. So therefore, we say our limit of this function as x approaches 2 is 4. And you could have simply just taken that 2 value, put it into the function, 2 squared is 4. We know that. When you put 2 in here, you get the y value of 4. That doesn't always work, though, so it's important to check the limit from both sides. Okay, so we say the limit is equal to 4. And you could have used any x value here. You could have said, what is the limit when x approaches 1, for example? And in that case, you'd be looking for this point right here, x equals 1. So what is the y value when you're approaching 1 from both sides? Well, the y value is also 1. So the limit, if this said 1, the limit would be 1. All right, this is convergent. It's converging on one value. It has a limit. Let's look at this one. So follow the same steps. Put this on your calculator, change your window to match this, and graph this and see what it looks like. Okay, hopefully you got a graph like this, and you should recognize this. This is a rational graph. We know that. We've been looking at rational curves recently. So here we can see there's an asymptote at x equals 5, and we can see that asymptote right here. So we know, again, when the denominator is 0, we have an asymptote. So we're going to check what happens when you do a limit when x approaches 5. So when you come from this side towards 5 and from this side towards an x value of 5, well, what happens? Check your table. So set the table feature and see if you can begin at 4.9 and see what you get. Well, here's the values I have. When x is approaching 5 from the left side, it can be 4.9, and I got a y value of negative 10. So if I'm at 4.9, I have a y value of negative 10. And if I have an x value of 4.99, so you're checking your table, we have a y value of negative 100. So basically that's saying what's happening here, this is going way, way down. So as you get closer to 5, this goes closer to negative infinity. It goes way down. Likewise, from the right side, as you approach 5, so when x is 5.1, the y value is 10. And when x is 5.01, the y value is 100. Again, it's going up, up, up as you get closer to 5. And then what does your calculator tell you when you go to x equals 5 in the table? Well, hopefully you see error in there. That error means, well, it doesn't exist. You cannot put 5 in here and get a value, right? It doesn't exist. We know that. There's an asymptote. There's a hole in the graph there. So it doesn't work. So therefore, there's a limit from one side, a limit from the other side. But at the actual point there's an error. But since the limits are different, because this is approaching positive infinity and this is approaching negative infinity, the limits are different. Therefore, this whole function, when we say x equals 5, we say the limit does not exist, because for the limit to exist, we need to approach the same value when we come from both sides. And in this case, we're not. We're approaching positive infinity this way and negative infinity this way. It's not the same value. It's not converging on one value. Therefore, the limit does not exist. Okay. And we also can say there's a discontinuity. That means like there's a hole in the graph at x equals 5. Okay, try this one. Graph this one. Set the window as you see here. Graph it. Let's see what it looks like. Okay, this graph looks like this. That's kind of strange. It looks like a line, even though this certainly does not look like a linear function. But we'll talk about this right now. So you graphed it, and there it is. And now we're looking for the limit as x approaches 1. So x approaches 1. So we're going close to this value here. So we're coming towards 1 from this side, we're coming towards 1 from this side, and we're seeing, does it approach the same value? And from the graph, it certainly looks like it. It looks like we're going to approach a y value of 2. So I'm already thinking the limit of this is 2, but let's see what we get. So I put in tables, so set your table to begin at 0.9, and then let's see what we get. So when x is 0.9, I got 1.9. What about when x is 0.99? That means really close to 1. It gives you 1.99, so you're getting very close to 2, which we can see on the graph. Okay, let's come from the other side. What happens when x is 1.1? Okay, that gives us a y value of 2.1, so as we're coming this way, we get a y value of 2.1, and then we get even closer, and that gives us a y value of 2.01. So notice as we come from both sides, we get close to 2. So check your table. When you get to 1 on the x-axis, do you get a y value? Oh, it says error again. That's strange, because this clearly seems to be coming together at the value of 2. So why at that spot is it not, why doesn't it work? Why don't we get an answer of 2? Because it seems to be coming towards 2. Well, here's why. Well, we know there's a x minus 1 in the function here. So what happens when you put 1, x value of 1 in here? You get a denominator that's 0, and that's undefined. That means there must be some kind of hole here in the graph, but I don't see it. So let's check our graph. If we check this on our calculator and adjust our window, I'll show you there's actually a hole there. Okay, so here's the graph that I graphed on this same window here, and it doesn't look like there's any problems at 1. But let's change the window and zoom in and see what happens. So I'm going to press window, and I'm going to zoom in right close to 1. So I'm going to make the x min like 0.99. And I'm going to make the x max just above 1. So let's say 1.01. So basically, I'm changing, so I'm going to be looking right close to that point here. I'm on either side of 1 here. Graph that, and look at what the graph shows us. So now we're zoomed way in on the line. So there's that line, and look, there's a hole. You can clearly see there's a hole right in the middle here. So there is a hole there at x equals 1. That's really interesting to see. So there is a discontinuity. We can mark it like this, but the limit still exists. the limit is still 2, because as you approach from either side, it's approaching 2. Even though it doesn't work at that point in particular, it's still approaching 2 from either side, so the limit exists.